Hey everyone, and welcome to today's Explainer. Today, we're taking a completely fresh look at a classic, frankly awesome coding challenge called matrix infection. This isn't just some abstract puzzle. It's actually a foundational pattern for mapping everything from social networks to real-world viral outbreaks. We're going to break it all down step by step, and in the process, shift our thinking from a rigid, boring 2D grid to a highly dynamic, expanding graph. So, here is the core question we're trying to answer today. Exactly how long until the entire grid is infected? I want you to treat this algorithm like a live, suspenseful simulation that we have to perfectly predict. We aren't just crunching numbers here. We're literally tracking an outbreak second by second across a constrained space. Every single tick of the clock matters, and our code needs to capture that spread flawlessly. Okay, let's dive into this. Here is our roadmap for today. First, we'll cover the matrix infection problem itself. Then we'll get into visualizing the graph, simulating one infection, moving on to multi-source BFS, dealing with unreachable cells, and finally, we'll wrap up with the complexity analysis. All right, Section 1, the matrix infection problem. Let's set up the rules of the game. Before we can actually track the spread, we need to know exactly how our virtual world works. So here are the ground rules for our matrix. Every single cell in our grid is assigned a specific state, represented by a simple number. A 0 means the cell is completely empty. A 1, that represents a healthy, uninfected cell. And a 2, well, that's an infected cell. Now, with each passing second, every infected cell spreads its infection to any healthy neighbors that are directly adjacent, in 4 directions: up, down, left, or right, no diagonals. Our ultimate goal is to write a piece of code that figures out the exact number of seconds required for all uninfected cells to get infected. Oh, and this is crucial. If the layout makes it impossible for every cell to get infected, we have to return -1. Just to make this super clear, check out how the spread looks in action. Notice the progression as we move from left to right. We start at second 0 on the far left with just a single infected cell. That number 2 right there in the middle. See how the infection pushes outward, strictly following that 4-directional rule? 1 second passes, and the cells directly above, below, and to the right turn into 2s. This chain reaction just keeps going until second 3 on the far right, where that final healthy cell up in the top left corner is finally overtaken. Let's move on to Section 2, visualizing the graph. This is where things get really cool. Now, what's really interesting here is the paradigm shift. On the left, sure, we have our standard everyday grid, but on the right, we've essentially popped those matrix cells out into a fully connected graph of nodes. The absolute secret weapon for solving this problem is realizing that every single infected and uninfected cell is just a node, and those 4-directional adjacency rules, they're simply the edges connecting them. And those empty zeros, they literally just don't exist in our graph. By dropping the empty space and just mapping the connections, the whole problem transforms. Since we're dealing with a graph now, we can pull out some classic graph traversal algorithms, specifically a level order traversal. If you weren't familiar, this is a breadth-first search, or BFS, method that explores a graph level by level, radiating outward from a starting node. Think about it. An infection spreading outward from a central point, hitting its immediate neighbors first before moving further out. It's literally perfectly modeled by this exact traversal. All right, Section 3, simulating one infection. Let's see this in motion. So, we start the clock at second 0, look at the graph visualization. We have our initial infected cell, our ground 0 node, marked right there in orange. In a standard breadth-first search, this node is the very first and currently the only item loaded into our processing queue. This is where everything begins. As we step into second 1, our algorithm dequeues that ground 0 node and immediately looks at its neighbors. Those neighbors, which are exactly a distance of 1 away from the initial infection, bam, they are now infected themselves, so they get added to the back of our queue. Visually, it's like a ripple moving outward in a pond. The pace keeps up at second 2. Now we process the nodes that were infected in the previous second. Their healthy neighbors are targeted next. This pushes the infection another whole level deep, to nodes that are a distance of 2 away from where we started. Our level order traversal is smoothly, systematically expanding the perimeter. And finally, at second 3, we process the last remaining layer in our queue. That final uninfected cell at the very end of the graph branch gets reached and infected. Our queue is now totally empty, the traversal is complete, and we know for sure our total time is 3 seconds. The graph model just handles the simulation beautifully, doesn't it? Okay, let's turn things up a notch. Section 4, Multi-Source BFS. Let's see how this builds when we have more than one starting point.
Look at the matrix here. We have infected 2s at 3 different coordinates. Now, if we just start a standard BFS from the very first 2 we find, the timing of our simulation is going to be completely wrong, right? Because in reality, the infection is spreading from all 3 of those locations at the exact same time. So the fix? We load all 3 of these coordinates into our queue right from the jump.
I really want to emphasize this because it's a crucial conceptual leap. A standard BFS begins with just a single root node in the queue, but we are upgrading to what's called a multi-source BFS. By scanning the entire matrix first and adding absolutely all initially infected cells to the queue before we even start the clock, we create a unified level 0. You can really see the power of this multi-source approach right here. Over on the left at second 0, we've got 3 separate ground 0 nodes scattered across our graph. Then, on the right at second 1, all 3 of those nodes expand outward simultaneously. We're tracking a multi-front spread in perfect synchrony, and it's all managed incredibly cleanly by our single queue.
But wait, what if things don't go perfectly? Section 5, Unreachable Cells.
Check out the bottom left corner here. We've got a healthy one that is entirely walled off by empty 0 spaces. Because our infection can only travel through 1s and 2s, this isolated cell is never going to get infected. It's completely safe. Our algorithm will run through its queue, finish up, and this cell will still just be sitting there. Now, remember our rules. If this happens, we have to return -1. But how do we catch this gracefully? We definitely don't want to horribly slow down our code by rescanning the entire matrix at the end just to check. So the really crucial point here is this highly elegant 3-step programmatic solution. Step 1, during that very first pass where we load our queue with the initial 2s, we just count how many 1s exist in the matrix. We keep a running tally. Step 2, during our multi-source BFS, every single time we successfully infect a cell, we simply subtract 1 from that tally. Step 3, when the BFS finishes, we literally just check our remaining count.
Let's walk through that tracking variable in action. On the left, during our initial scan, our queue gets loaded up, and our counter is set to 3 because there are 3 healthy cells. On the right, our BFS has completed, but notice we only managed to infect 2 of those cells. Our counter went down twice, leaving our variable equal to 1. Because 1 is greater than 0, we instantly know an uninfected cell is still out there, which triggers our required return value of -1. Bam! No rescanning required.
Finally, let's bring it all home with Section 6, Complexity Analysis. This is what really matters in an interview or a real-world system. Now that we've built this bulletproof algorithm, let's look at the final verdict on performance. Our time complexity is big O of m times n, where m is the number of rows and n is the number of columns. This is because, in the absolute worst-case scenario, our level order traversal is going to explore every single cell in the matrix. Space complexity, it's exactly identical, O of m times n. This is primarily dictated by our queue, which, again in the worst case, might have to hold almost every cell in the grid all at once. So both time and space scale linearly with the size of the grid, which is highly optimal for this kind of simulation. So we've successfully transformed a static 2D grid into a dynamic graph, and we tamed it using a multi-source BFS. But before we wrap up this explainer, I want to leave you with something to really chew on. If you can perfectly model this infection in 2 dimensions using 4-directional adjacency, how would you adapt this exact same queue logic for a 3D grid? Seriously, think about the axes, think about the neighbors, and think about how powerfully this simple algorithmic pattern can scale. Thanks for joining me on this explainer, and keep exploring.